Welcome to my Computer Architecture Fundamentals series, where I'll be going from the fundamentals of computer architecture, hopefully all the way up to a couple basic processor implementations and maybe some more complex theoretical stuff. In some of my other videos, I covered logic gates as well as hardware descriptive language programming. I recommend to go check those out. You don't necessarily have to do those first. You can watch the three fundamentals videos in any order, but I would recommend this and logic gates at least before your hardware descriptive language. Um, Assembly can be thrown in wherever you want, and this video is on assembly. So assembly is the most basic level instruction that your computer executes. So when you write C code and you compile it, you're compiling it. It first gets compiled into assembly before it gets assembled. This is like the last final step before it becomes machine readable. Um, and while machine readable code is kind of readable as a human, it's not very efficient because you're looking at a bunch of numbers, and unless you can memorize assembly like opcodes and everything into numbers like a computer can, you're not going to be able to read the assembled code very well, which is why we have assembly, as this is just one step away from actually executing. I'm going to be going over RISC-V assembly. It's a very simplistic assembly architecture. You can do some pretty advanced stuff with it, but we'll stick to some of the more basic stuff for this fundamentals video. So what is RISC and why? RISC stands for Reduced Instruction Set Architecture. RISC architectures use a simplified set of instructions, as I said before. These typically execute in a single clock cycle, which allows for more pipelining and higher overall throughput compared to complex instruction set architecture. This has the added benefit that if this is on like an embedded system like your phone or like a laptop or even like a drone, reduced instruction set architecture uses less power because these are much more simple instructions. Now, this does mean that RISC might be a little bit slower at more complex tasks like 3D rendering that require large amounts of multiplications. I mean, you're going to see a lot more additions, subtractions, basic logic operations on a RISC architecture rather than like multiplies, divides, square roots. You're not going to see those kinds of instructions on a RISC architecture. So there are a couple RISC-V instruction types. Probably the most important are your R-type, I-type, and J-type, as the other three are kind of similar to the other ones. So for your R-type instructions, you can think of this as register to register. So it performs a logical operation using two source registers and then outputs it into a destination register. Your immediate operations are similar, but it just uses one source register and a 12-bit immediate value, as well as it outputs it to a destination. So effectively, you can add one register plus whatever magic value you need, like a 2, 4, whatever. Those can be helpful for initializing your programs or initializing values, because your zero register, and this is important, your zero register will always be zero. Even if you try to write to it, it should always remain zero. There are multiple ways to keep it at zero. You can either have the write enable always be low. You can always keep the reset high. There's a lot of different ways that you can keep it zero in hardware, but you need the zero register to remain zero because when you initialize your program, you don't know what's in all the registers. You can reset them sometimes you can't. So just having that zero register makes it possible to set your register values to zero. You have your store type instructions, your S type. Those take a value from a register and then they compute an address, which is your source register 1 plus assign extended immediate, and then it stores it. It stores like a word, a byte, half word. We'll look at just storing words. We'll use a word addressable memory later on. Um, you have your branch operations. Um, you compare two source registers. If the condition is true, like if they're equal or not equal, if one is greater than or less than the other, then it will jump to a PC relative offset. So it's effectively an immediate. This gets encoded in your assembly as a label, a human readable label, which when assembled will effectively give you your relative position to that label. So it depends on how, like, if you need to jump up 4 lines or down 4 lines, it gives you that immediate. You have your upper immediate U-type instructions. It's similar to your add-I, but it loads a 20-bit immediate that is shifted left 12 bits, so it loads the upper 20 bits. And then finally, you have your J-type, which are your jumps. So these are unconditional. This is if you do like a function call and you jump to, like if you have a function that adds two values together, it will always jump to that function and it will store the return address so that it knows where it has to jump back to after it finishes that function call. Now, for manual assembly, which this will be helpful for debugging because you'll be able to take your assembly code and you'll be able to manually gather the opcode and all the fields. You need to first identify the instruction type, so R, I, S, B, U, or J, based on the mnemonic. And the mnemonic is just the instruction name, so your add-I, store word, SW, all those. You look up your fixed fields, so you have your opcode, your function 3, and function 7 for certain instruction types from your RISC-V specification. I'd recommend to have what's called a green card. It's basically just all of the opcodes, function calls, and a bunch of other very helpful information on hand. RISC-V has 32 registers encoded as a 5-bit value. It counts up from 0 to 32, or 0 to 31, sorry. Next, you can handle your immediate value if it's an I-type or a U-type or a store word type, and sign extend it or zero extend it, depending on what operation you're doing. But typically, you'll sign extend, and then you'll split your place bits according to the type's format. And I can't describe it perfectly well here, but if you look at the RISC-V specification, you'll notice that a bunch of different instructions that use immediates have those or you have your immediate value bits just spread all over the instruction encoding. And that's for a good reason. It makes it easier for them to create 16-bit instructions, but it does make the instructions look a little bit weird because you have your immediate values spread across 3 different areas and then you have to concatenate it together. Can be a little annoying. And then finally, you can fill it in, most significant bit to least significant bit, and then convert it to hex. The reason you want it in hex is it'll just be a lot easier to read because you'll have a lot less values because it'll be 32 ones and zeros, or just an 8 hexadecimal values or 4 hexadecimal values or whatever it is. And I have some example assembly programs. These example assembly programs have a basic add sequence. So it'll first load 10 into the register 1, and then it'll add register 1 to 5, which will output 15. Then it'll add -8, which will give you 7. Add 100, 107. Add it with 0 to another register, outputs 107. Now this dot text, basically it's important for assembly because this defines your program, is your dot text. This is what gets loaded into your instruction memory. Main, global, this is just for the linker. Generally, it's not needed. It's just an artifact. And then you have your WFI, which is your halt command, aka your exit statement, effectively. Sometimes it's just an infinite loop depending on the program, but for this case, we just terminate the program here. So that's your like a basic add sequence. I would pay attention to how these increment from 0 to 5. And it is important to note that while this is incremented 0 to 5, you do have registers like T2, T3. Those are your temporary registers. Look over it on the green card. In practice, when you're actually writing programs, you probably won't want to do something like this because these registers will often have specific purposes to them, like a stack pointer that points to a certain memory address, or are used as like function call passes. This next example actually does use these temporary registers. This is just a basic for loop. It starts off at main, it loads some immediate values, it starts the loop. If T0 and T1 are equal, it exits, but because you have 0 and 100, it'll increment the counter, increment I. You can think of T0 as I, T1 as your loop limit, so I is equal to 0, while I is not equal to 100, I++, that's the C or any other programming language for loop equivalent. And this will just jump back to the loop, jump back to the loop, jump back, and then once it's finally done, once it's equal to 100, it'll branch and jump here and terminate. So that's like a basic for loop in assembly. And finally, I have a load store program. This is a bit more complicated. Loading and storing can be complicated, and this is specifically loading and storing words. So it's not storing specific bytes, it's storing 4 bytes of data at a time. So this will load the address of data. This is basically, if you're using some kind of like assembly simulator, like RARS, RARS is the only one I know of, but if you're using some kind of assembly, either simulator or actually running RISC-V assembly on the RISC-V processor, this data section is loaded into memory. So this is in memory, this is in memory, this is in memory, but it's inaccessible directly. But if you load this is load address of data, this is your section data, and then it loads the address into T0. So it starts off here, location 0. And then it loads the 3 words. It uses T4 as a temporary register. This is the move instruction. So this basically just swaps T1 and T4. And then this swaps, and then this swaps. And then we do an XOR swap. Basically an additional little trick here. And then it finally stores the words back into memory. And you can see that it's in a completely different order. It starts 42, 123 to 7, and now it's 123, 7, 42. And then after it does the whole section, it terminates. So that's all I have for some basic assembly. Obviously, you can see that for some very basic instructions, it can get pretty verbose. I think loops especially can get kind of confusing because you might have to invert your like initial condition for when you continue the loop, just because the behavior is slightly different. But generally speaking, this is all I have, so good luck and have fun.